Dear friends, welcome back. In our previous lecture, we discussed about how to estimate the power required for various cases as well as the thrust required, and we figured out what is the minimum power required and minimum thrust requirement of the system as well as the maximum velocity that at which you can fly with a given power plant. And we also witnessed about what is the stable region of flight and what is unstable region of flight. So, what is the whole idea behind behind this exercise? Otherwise, say how can you select a power plant for a given UAV, right? So, as mentioned earlier, we need to figure out what is the corresponding requirement of the system during various phases of flight. Now, since we discussed about level flight, which is the cruise here, steady level flight, let us figure out a power plant of a UAV by taking an example. Find the specifications of the power plant. For the following delta wing UAV during its cruise. Say the span of the UAV 1.5 meters, the root chord is 0.9 meters, tip chord is 15 centimeters, and say wing loading 447 kg per meter square. And the drag polar of this UAV is 0.035 plus kcl square. Assume Noswell's efficiency of 0.666. 0.686. So, the maximum velocity at which the maximum velocity of flight this UAV has to fly is 35 meters per second. From wind tunnel testing, the CL max of this configuration is 1.01 at approximately alpha stall of 21 degrees. And you can also right. So, find the specifications of the propeller driven engine for the following delta wing UAV during its cruise. The maximum velocity of flight that is expected from this UAV is 35 meters per second. Now, given the span of the system, the span of the wing, they say it is a delta wing UAV, it has 1.5 meter span and a root chord of 0.9 meters and a tip chord of 0.15 meters. And say this is 0.9, this is 0.75, right, and the Oswald's efficiency factor. So, B is 1.5, CR is 0.9, CT in this case is 0.15. And wing loading is given W by S, right. W by S is 4.447 kg per meter square, kg per meter square. And we assume that this UAV has to perform its flight at sea level, right. So, we can assume flight at sea level. So, density at sea level is 1.225 kg per meter cube. And the drag polar is given for this UAV, which is CD naught plus KCL square is equals to 0.035 plus K into CL square. So, this implies CD naught, the profile drag coefficient is 0.035, and we need to find out what is K, induced drag correction factor. Now, we need to understand like what should be the power plant specifications. That means, so one of the mission requirement is that the maximum velocity is 35 meters per second. So, we know that from our previous lecture, we can refer to our previous lecture and say, so if this is a power required and this is your velocity, so this has a typical variation, right. This curve represents the typical variation of power required with velocity, and say if this is your power available, which almost remains constant with velocity for a propeller driven aircraft, right. So, if power available and power required. So, we need to mention what is the maximum power required by the required by the system, right. So, if you know the maximum power required by the system, then we can say that this amount of power has to be delivered by the power plant, propeller as well as engine combination, right. So, if we come up with these specifications like what is the power available, we will be able to specify the corresponding power plant, right. So, say this is your Vmax, which in our case is 35 meters per second. So, you need to find out this power, this point of intersection, right. So, for this power required, if power available at that point is equals to power available max. So, because this is your maximum velocity, right. So, this should be your power available maximum, or say that may not be necessary, but you can say take a factor of safety and you can use it. That may not be the maximum capability of the engine itself, but this should be the required power that need to be delivered by the power plant to the system to achieve the level flight at this required velocity. Right. So, the maximum velocity we require is 35 meters per second. So, power required at V is equals to 35 meters per second, that is equals to drag into velocity which is 35 meters per second in this case. So, half rho V infinity cube S into CD. So, this equals to half rho V infinity cube S into CD naught plus KCL square. Now, what are unknowns here? S is unknown. Yeah, S we need to find out. K we need to find out, alright, and CL for this velocity, right. Okay, how to find that? So, S is equals to B into CR plus CT by 2, which is CR by 2 into 1 plus lambda, right. So, what is lambda? Where lambda is equals to CT by CR, which is 0.15 divided by 0.9, lambda is equals to 1.667, 0.167, 0.1667, not 0.167, right. So, this is your lambda. Please substitute lambda here, and you know what is CR. CR is given as an input here, 0.9 meters, and B is 1.5 meters. So, 1.5 times 0.9 by 2 plus 1 plus 0.1667. This implies S is equals to approximately 0.787 meter square, right. We got to know what is the area here, right. And if you want to find out what is the weight of this UAV, wing loading is given, right. W by S is equals to 447 kg per meter square. This implies W is equals to 4.447 into what is S? 0.787. This implies W is approximately 3.5 kgs, right. So, the weight of this UAV is approximately 3.5 kg. Now, you have area with you and you know density. What is K? K for this UAV is 1 by pi EAR. So, what is K? Pi into, so the Ostwald's efficiency is given here, which is 0.666, which is 0.686. So, the Ostwald's efficiency is given as 0.686 for this configuration. And what is the aspect ratio? Aspect ratio is equals to B square by S, right. That implies B is 1.5 meter square by 0.787 is equals to 2.85. So, substitute that aspect ratio here, 2.85. K is approximately 0.16, right. Now, we have K here. Now, we need to find out what is the corresponding CL. How do you find CL? We have from equation C2, since it is a level flight, right, we are talking about level flight. So, during level flight, thrust is equals to drag of the system and lift is equals to weight of the system. So, since C2 L is equals to W, which is CL is equals to twice the wing loading by rho into corresponding velocity square. So, if you want to fly at the maximum velocity, or the maximum velocity that UAV has to perform is has to fly is at 35 meters per second. So, substitute 35 meters per second here, and you have the corresponding wing loading data, and you know what is density of flight. right, the altitude of flight where you can find the corresponding density, and you can figure out what is the corresponding CL for this configuration, CL for this particular flight. So, CL for this particular velocity 35 meters per second is equals to square root over 2 times W by S is 4.4447, it's kg per meter square, right. So, but W is in, it should be in Newton, right, it is force. So, convert this to Newton per meter square divided by 1.225 is the density since we are flying at sea level, and what is corresponding velocity is 35 meter per second square. This equals to 0.058. See, the CL required for this particular flight is 0.058, which is very, very less, right. What you have to find out is power available is equals to power required at V is equals to 35 meters per second, 35 meters per second, which is equals to half rho V infinity square S into CD naught plus K CL square. This equals to half into 1.225 into 35 into V infinity. This becomes 35 cube into 0.787 into CD naught is 0.035 plus 0.16 into CL square, 0.058 square. So, this equals to 733.691 watts. This is the power that is required by the system. The system demands, the UAV demands a power of 734 watts when you are flying at a velocity of 35 meters per second during cruise. So, this is the power available, right. But what we get as an output is a shaft power from the engine. So, the engine is rated in terms of shaft power, right. PSH is a shaft power, right. So, when the shaft is combined with a propeller, you will get the corresponding useful power, right. So, propeller efficiency is given as 0.9, and we know power available is equals to efficiency times shaft power. So, what should the corresponding shaft power that the engine has to deliver? Is power available by eta propeller efficiency, which is 733.691 watts divided by 0.9 is the propeller efficiency that is given into 0.9, 815.21 watts. So, you have to select a power plant which gives at least 815.21 watts if you want to move at 35 meters per second. But ideally this should not be at the peak power of the IC engine or the whatever the power plant that you select. It should be, so you need to get this peak power at a 50% of what it is rated for. Say if your power plant peak power is rated about 1200 or so, then this will be about 60% of it or 70%. So, that should be a good number to select, right. So, you need to select a power plant which delivers this power at 60 or 50 to 60% of its rated power. So, this now let us extend this question a bit. So, you have figured out what is the shaft power, right. Now, how do you get to know like what can be the minimum velocity that I can fly, at the same time what can be the corresponding minimum power that that the system requires, right. Power requirement of the system of this UAV. How do you get this? You need to find first what should be the velocity, right? So, you know what is the range of velocities that you can fly? Do you know it or not? What should be the range of velocities? Either velocity for minimum power required or stall velocity, right? And the upper limit is maximum velocity that you want. So, let us find out the lower limit of this velocity range. So, for that we need to find out two velocities, either the stall velocity as well as both the stall velocity and minimum velocity for minimum power required. Now, let us see what is the velocity for minimum power required. Power required minimum, which you can attain by velocity for CL power 3 by 2 by CD maximum, right, which is equals to square root over 2 twice the wing loading divided by density into CL for power required minimum, which is CL power 3 by 2 by CD maximum, right. This equation we got it from C2, L is equals to W, right, lift is equals to weight in this case, since it is a cruise. So, what is the corresponding velocity for power required minimum? So, to get this we need to know what is CL for minimum power requirement condition, which is CL for CL power 3 by 2 by CD maximum, right. So, what is that condition? CL for power required minimum is equals to CL for CL power 3 by 2 by CD maximum, which is equals to square root over 3 CD naught by K. So, this implies CL for CL power 3 by 2 by CD maximum is equals to square root over 3 into what is CD naught? 0.035, which we obtained it from drag polar, and K we have calculated, which is 0.16. So, this turns out to be 0.81. See, the CL almost demands, see the maximum CL we got, we have it is about 1.01, right. So, we need to fly almost close to stall angle of attack. So, as the velocity decreases, the corresponding requirement of CL increases, right. We need to trim at higher angles of attack. Now, substitute this value here, twice wing loading. What is wing loading? 4.447 into 9.81, because 4.447 is given in Newton kg per meter square, we need to convert that to Newton per meter square. Density is 1.225 sea level density kg per meter cube, and the corresponding CL for this condition is 0.81. So, this turns out to be approximately 10.37 meter per second, right. So, this is the velocity at which you need to fly if you want to maintain a minimum power requirement condition. But is this velocity possible? We have to check. If it is less than the stall velocity, then you will not be able to fly, right. You will not be able to fly in a level flight condition. Now, we need to find out what is the stall velocity as well. V minimum is obtained later. So, stall velocity is square root over twice W by S by rho into CL max. So, CL max is twice W by S is 4.447 into 9.81 into 1.225 into CL max is 1.01, 8.39 meters per second. So, V minimum is equals to V stall, since V for power required, no, V minimum is equals to V for minimum power requirement, power required minimum is equals to 10.37 meters per second. Why? Because power required minimum is greater than V stall. That means, so V stall falls in the region of unstable flight, right, region of velocity region of unstable flight, right. So, that is why we have to fly at V for minimum power required condition. So, we can straightforward say that, right, because the CL for this condition is 0.81, but CL max is 1.01. That means CL for minimum power requirement is less than CL max. That means in the denominator this quantity is lesser than the other quantity, which means the velocity will be higher. So, we can straight away say that we can fly at minimum power requirement. So, we have estimated the minimum power, minimum velocity of flight, and what should be the corresponding power required by the system. So, power required by the system is equals to, or power required minimum, right, this is the velocity for minimum power required, is equals to drag times velocity, which is half rho S CD naught plus KCL square into velocity for power required minimum square, and CL for power required minimum, sorry, it is cube, please correct this is cube, because half rho V square and V infinity, it is cube. So, CD naught plus K CL square, CL for power requirement minimum condition. So, 0.5 into 1.225 into 0.787 into 0.035 plus 0.16 into 0.81 square. So, this is your CL for minimum power requirement condition. So, you need to substitute this value here, or say, so you need to substitute this value, in this equation. 0.81 square times, and the corresponding velocity for minimum power requirement is 10.37, right. This is the corresponding velocity for minimum power requirement. .37 cube, this equals to 75.24 watts. See, for maximum velocity you need around 734 watts, and for minimum velocity condition you require 75 watts. Now, let us look at another example. The same question, let us solve for a jet engine. Find the specifications of the jet engine for the following delta wing UAV during its cruise. The maximum velocity of flight that this UAV has to fly is 35 meters per second, right. So, again here, similar to that propeller driven aircraft, we need to find out, in this case the jet engine is rated in terms of thrust, right. In propeller driven aircraft it is rated in terms of power. So, we need to find out what is the maximum thrust requirement, or say here, since the maximum thrust requirement comes when you fly at the maximum velocity. For this case, the maximum velocity that is required as per the mission is 35 meters per second. So, we need to find out the corresponding thrust required at 35 meters per second, and the jet engine need to deliver the thrust at 35 meters per second to achieve this particular flight condition. Let us see how to proceed this problem. So, what we have from C1 for level flight, thrust required is equals to drag, right. If you look at thrust versus velocity, variation of thrust and velocity, say in Newton or kilonewton, say it is meters per second. Now, the typical plot for thrust required velocity is this one, which is thrust required is nothing but drag here. So, this is the thrust required. and say this is your thrust available from the engine, right. Now, what is this plot? Thrust required and velocity. It's a summation of, which is nothing but drag in this case, right. For a level flight case, this thrust required is drag, which is a summation of profile drag and induced drag, right. So, induced drag will be lower or at higher velocities, right. So, as the velocity increases, this is profile drag. So, as the velocity increases, the profile drag increases and the induced drag decreases. This is induced drag curve, right. So, this intersection where CD naught is equals to CDI. So, this is like half rho v square S CD naught, right, and this is half rho v square S into K CL square. KCL square we can term it as CDI, coefficient of induced drag. So, at this point these two coefficients are equal, like, so this point corresponds to CD naught is equals to CDI, that is equals to K into CL square, right. So, KCL square is equals to CD naught. So, the total drag coefficient at this point, is 2 CD naught. CD is equals to 2 CD naught at this particular point. So, this is the condition for when this is achieved, when you are flying at L by D maximum. So, the corresponding velocity is velocity for TR minimum or L by D maximum. So, this point corresponds to thrust required minimum, right. Yeah. And when do we achieve maximum velocity? So, when thrust required is equals to drag, right. Thrust required is equals to thrust available from the power plant. So, this particular velocity will be the maximum velocity of flight, and this corresponds, for this particular case it is 35 meters per second. So, if this is the case, what should be your thrust requirement? That is the problem that we need to solve, right. So, what we have is from C2, from C1, what we have is thrust is equals to drag, and we know thrust required is equals to W by L by D, which we have solved earlier, W by CL by CD. So, for maximum TR max, if you or TR at velocity 35 meters per second is equals to W by CL for 35 meters per second or CL by CD for 35 meters per second at velocity 35 meters per second. Right. So, what is the weight of this system, which we have earlier calculated? So, wing loading here is 4.447 kg per meter square, and the area we figured it out as 0.787 meter square, and aspect ratio is 2.885, and Oswald's efficiency is given as 0.686. So, the corresponding induced correction factor induced drag correction factor is 0.16, right. And from the drag polar we have CD naught is equals to 0.035, drag polar we have CD naught is equals to, right. So, what will be the CL for 35 meters per second? From C1, C2, we have L is equals to W, which is half rho V square, SCL is equals to W. We have CL for this particular case when V infinity is 35 meters per second, 35 meter per second is equals to twice the wing loading divided by density at the respective altitude into the corresponding velocity of flight, which in this case is 35 meters per second. This implies CL for this velocity, or which is considered the maximum velocity for this UAV, 35 meters per second. As per the mission requirements, 35 meters per second is the maximum velocity. Right. This is twice the wing loading, which is 4.447 into 9.81. We'll convert this to Newton per meter square divided by 1.225 kg per meter cube into 35 meters per second square. The corresponding CL for V infinity 35 meters per second is 0.058. So, this is not going to change, right? We have earlier calculated this. This is not going to change. Either the jet engine or the propeller engine, driven engine, that is not going to change any CL requirement because you are flying at cruise. See, the propulsion system, whatever the way it is, ultimately we need thrust, right? Whether it is generated by an electric driven engine or a propeller driven engine or a jet engine. What you have is CL here, which is 0.058. Now, using this CL, we can calculate what is CD. CD for this case is at V infinity 35 meters per second is equals to CD naught plus KCL square. It should also remains the same. What is the value? 0.035 plus what is K? 0.16 into CL square, which is 0.058. So, 0.0355, which we have earlier derived, right? This is exactly same. CD at V infinity 35 meters per. So, please make a correction. It is 0.0355, right? So, what is L by D of this configuration? No, at this particular flight condition, what is the L by D at that particular flight condition? So, L by D at V infinity 35 meters per second is equals to CL by CD at V infinity 35 meters per second, which is equals to CL at 35 meters per second and CD at 35 meters per second, which is 0.058 divided by 0.0355, 1.6338. Reason why L by D for delta wings is very less, right? In other cases it would have been at least 16, 14. In delta wings it is like 1.6 because the profile drag is very high for this delta wings. The thrust required. So, this should be the thrust available, which is equals to W by L by D at 35 meters per second at velocity. This is W is W is 3.5 kg into 9.81 divided by 1.6338. 21.015 newtons, which is approximately 2 kgs of thrust. You need to give 2 kgs of thrust to lift a UAV of 3.5 kg if you want to move at 35 meters per second with this particular drag polar. Right? So, this should be the amount of thrust that this engine has to develop. Now, what should be the minimum thrust requirement? Thrust required minimum is equals to W by L by D maximum. So, this should be the minimum amount of thrust you need to supply in order to achieve a level flight for this particular UAV, right. 3.5 into 9.81 into what is L by D max, root over 4K CD naught. 3.5 into 9.81 into square root over 4 into 0.16 into 0.035. 5.138. So, you need to fly at 5.138 newtons, which is approximately 0.5 kg, right, that is 500 grams. You need to supply 500 grams of thrust if you are flying at L by D maximum, right. What is L by D max here? Now, let us look at what is L by D max for this case. What is L by D max? That is CL by CD max, which is 1 by root over 4K CD naught, that is 1 divided by the root over 4 into 0.16 into 0.035. So, this value is 6.681. So, see, the L by D max for this configuration is 6.618, whereas the L by D in this particular case is 1.6, approximately 1.6, right, 1.64. CL for L by D max, root over CD naught by K, which is root over 0.035 divided by 0.16, which is 0.4677, right. See, this is the CL for this particular case, and the CL for, see, you are flying at minimum velocity. Minimum thrust requirement is like minimum velocity for this flight. Why? Because the corresponding velocity of flight we haven't calculated. Let us look at that, then we can comment it again. So, the CL for L by D max is 0.4677, right. And what is CD? CD naught plus KCL square, so which is 2 CD naught, it's like twice 0.035, it is 0.07, right. This is the value of drag coefficient at this particular flight. So, how to achieve this? You need to trim at the corresponding angle of attack. Now, what is the velocity for this thrust required minimum condition? Is equals to square root of twice W by S. This is from C2. Using C2 equations, you can find it out. Since lift is equals to weight, 2W by rho, 2W by S by rho into corresponding CL for L by D max. Twice, what is the wing loading here? 4.447 into 9.81 divided by 1.225 into what is CL for L by D max is 0.4677. 12.340 meter per second, 12 meters per second approximately. So, you need to fly at 12 meters per second. The CL here is, CL for L by D max is 0.467, right, whereas CL max is 1.01. So, since this is lesser than CL max, the stall velocity is lesser than V here, because this is in the denominator, right. So, you will have this velocity will be higher than the stall velocity, and we have also calculated stall velocity as 8.2 meters per second, right, in our earlier in the earlier example we solved for stall velocity, that is not going to change whether you are using a jet engine or propeller engine, right. So, the velocity for minimum thrust requirement is 12.34. So, this is your boundary for stable flight, right, velocity regime for stable flight. So, this is the minimum limit. So, the maximum limit that you already specified as per the mission requirements, which is 35 meters per second. So, you have a velocity range of 12 to 35 meters per second using this jet aircraft, right. So, see as the velocity decrease, the CL value for the corresponding CL value has increased here, right. Here the CL value is very less, but the velocity is high. So, the profile drag is higher, that is why L by D is lesser. Let us look at another example. A flying wing weighs 22,000 kg, has a NACA NACA 653-418 airfoil with a wing area of 30 meters square and aspect ratio 5. Determine the angle of attack when flying at 60 meters per second, say 60 meters per second, when flying at 60 meters per second. Find the corresponding L by lift to drag ratio consider CL alpha of airfoil 2D, CL alpha 2D, or for the airfoil is 0.106 per degree, and CD naught is 0.000043 and comma CD naught, and E is 0.996. So, consider E as 0.92, okay, 96 is too high. So, this is the data that is given. So, there is a flying wing UAV which weighs about 2000 kg and it is flying at a velocity of 60 meters per second at sea level. Assume it is flying at sea level, right. So, it has an aspect ratio wing area of 30 meters square and an aspect ratio of 5. So, we need to determine the corresponding angle of attack of flight. At the same time, what is the L by D of this flight. So, the other data that is given is we have CL alpha 2D as 0.16 and CD naught is 0.043 and E as 0.92, right. How do we determine trim angle of attack? First, we need to know what is the corresponding CL solution. First, given W is equals to 2000 kg, which is approximately equal to 20,000 Newton, right, W multiplied by approximately 10, right, 9.81, and S is given as 30 meters square and AR is given as 5 and E is 0.92. And the velocity, cruise velocity V infinity is equals to 60 meters per second, right. At the same time, the CD naught of the wing is given as 0.0043 and CL alpha of wing, CL alpha of airfoil, that is 2D, which is let us say A naught is the airfoil CL alpha, which is equals to 0.106 per degree right. We can convert into radians, right, 0.106 into 180 by pi, 6.073, 6.033 per radian. This is a CL alpha 2D of 2D, that is a CL alpha of the airfoil. Now, how to find out CL alpha trim for this particular case? That means when you are flying at 60 meters per second, how do you get the alpha trim of the UAV? During cruise, we have from C to lift is equals to weight, that is it should be half rho V square S CL is equals to weight, right. So, this should be your CL during cruise, that is 2W by S divided by, so what is this? W is 20,000 newtons divided by S is 30 meters square divided by 1.225 into 60 square, 3600, 0.302. 0.302 is your CL for this corresponding flight, right. So, assuming a linear range of angle of attack, the CL design or CL for this particular flight condition is equals to CL naught plus CL alpha of wing into alpha trim. So, how to attain this is like alpha trim is equals to CL for this current condition divided by minus CL naught over CL alpha of 3D. Now, what we need to find CL alpha and CL naught of the wing, right. If you know what is CL alpha of the wing and CL naught of the wing, you will be able to find out the corresponding trim angle of attack. Now, how to find the CL alpha of the wing? We have the relationship, right. We derived it earlier. CL alpha 3D or for wing is equals to CL alpha 2D divided by 1 plus CL alpha divided by pi E AR. This implies CL alpha 3D is equals to, what is CL alpha 2D in this case? 6.0733 divided by 1 plus, this is your CL alpha 3D per radian, 2D of NACA 653418004. .0733 divided by pi E 0.92 into aspect ratio of 5. CL alpha 3D is equals to 4.276 per radian. So, this is a corresponding lift curve slope of wing, right, of this. We need to find CL naught of the wing. How can you find? Minus CL alpha 3D into alpha trim minus alpha at which CL is 0, which will be same for both the cases. Since we do not have the information about alpha at which CL is equals to 0, we can consider this entire angle of attack as angle of attack with respect to 0 lift line. So, we got CL alpha from here. We know alpha trim, if we want to find out the corresponding angle of attack of trim to achieve this CL, what we need is CL naught, since we got CL alpha from here. So, how to find CL naught of this wing is minus CL alpha into alpha at which CL is equals to 0. For 635,418 from our previous lectures, you can refer those previous lectures. The alpha at which CL is equals to 0 for aerofoil is minus 2 degrees, approximately minus 2 degrees. So, since alpha at CL 0 remains same for, it is an assumption that we consider remains same for both aerofoil and wing. So, assuming that minus 2 degrees here, what we have is minus 4.276 into minus 2 into pi by 180. 0.1492. So, CL naught is 0.1492. So, now the corresponding alpha to trim is equals to, from this equation, which is CL minus alpha CL trim minus CL naught divided by CL alpha. This equals to alpha trim is equals to CL is 0.302 minus 0.1492 divided by CL alpha is 4.276. This equals to 0.0357 radians, which is approximately 2 degrees. Right? This is the angle of attack at which you need to trim this UAV, a 2000 kg UAV, if you are flying at 60 meters per second with this particular drag pool. Now, if you want to find out L by D for this particular flight condition, you have CL and CD for this particular flight condition, which is CL is 0.302 by CD is CD naught plus KCL square. K you can find out, you have aspect ratio and Oswald's efficiency. What is K? K is 1 by pi ER. K is 1 by pi ER. That implies K is equals to 1 by pi into 0.92 into aspect ratio of 5. 0.0691 K, value of K. So, substitute that value of K here, 0.302 divided by CD naught is 0.0043 plus K is 0.0691 into 0.3, otherwise CL trim square. This equals to 28.51. Right. So, L by D for this particular flight condition is 28.51. So, this UAV is flying at an L by D of 28.5. Although it is a low aspect ratio wing, still this profile drag is very less for this.